taking an imaginary equation where A plus B forms C plus D, where the capital letters are the generic chemicals and the little letters are the coefficients. We express what's called an equilibrium constant that compares the amounts of products to the amounts of reactants. So even though the concentrations of reactants and products are not equal, there is a relationship between them. And that relationship is expressed in the terms of law of mass action. In general, for the equation A plus B forming C plus D, capital A, capital B are our reactants, little a, little b are their coefficients. Capital C, capital D are our products, with little c and little d as our coefficients. The law of mass action is an expression that gives the relationship below. The concentration, that's what these brackets mean, are molarity units. The concentration of product C raised to the power of the coefficient times the concentration of product D raised to the power of its coefficient, set over the reactant A to its power and reactant B to its power. This is known as the equilibrium constant, products over reactants, where where coefficients become the superscripts, the powers in which we raise those values. The equilibrium constant is a number. It does not have a unit. It's the magnitude of the number that's of interest to a chemist. The larger the equilibrium constant, the more products we have in that ratio. The smaller the equilibrium constant, the more reactants we have. So the equilibrium constant is a ratio of products over reactants, and it's a number. The size of the number itself gives us great insight into whether we're favoring the product side or favoring the reactant side. Products over reactants, where the coefficients become the powers with which we raise our concentrations of reactants and products. So for the reaction where A plus B makes C plus D, notice that these are all aqueous, so they have a molarity unit. The equilibrium constant, often I see that as EQ. KEQ is what you're going to see me write if I do this. Later on we'll have KAs for acids, KBs for bases, KSPs for solubility products of salt. KEQ, equilibrium constant, is a general way of writing any specific value here. We'll later talk about KC for concentration units, or KP if we're using atmospheres. So technically, since these are brackets, the correct word here is KC for concentration units known as molarity. Equilibrium constants can be for acids, they can be for bases, they can be for salts. They can use concentration units like molarity. They can use atmospheres or torr or millimeter of mercury if we're looking at pressures of gases. So products over reactants, the coefficients become the powers. So in this example, suppose we read in the forward direction, 2 N2O5s is in equilibrium with 4 units of NO2 and 1 unit of oxygen. The coefficients become the powers with which we raise. So notice in a bracket, the bracket stands for molarity units. The concentration of nitrogen dioxide raised to the 4th power times the concentration of the oxygen molecule raised to the 1st power set over the concentration of N2O5 squared. The brackets are standing for molarity. The coefficients become the powers with which we raise those values to. Products over reactants, coefficients become powers. So what does the value of this equilibrium constant imply? The larger the equilibrium value, we now know that when the reaction reaches equilibrium, we favor the product side. In other words, if it's greater than 1, and the larger it is greater than 1, the more product that we're actually creating. To think about that, I would favor the product side, showing an equilibrium arrow that if this indeed has a greater value than this, it makes sense that when we put products over reactants, we're going to get a number bigger than 1. And the opposite is true. If the equilibrium is favoring the reactants and we put products over reactants, and we start favoring the left side of the arrow, we have a small number placed over a larger number. If I favor the reactant side, we're going to get an equilibrium constant much less than 1. So it's the number itself that's of interest. We can tell by the magnitude of the number how large or how small if we have a lot of product compared or if we have a lot of reactant compared to the other. And if indeed equilibrium constant is exactly 1, we have the same amount of reactants and products. So a large equilibrium constant. If I take a look at this particular equation where hydrogen and bromine form hydrogen bromide, and I'm looking at the amount, I have 1 hydrogen, 1 bromine, and a whole lot of HBr in this particular diagram. The hydrogen molecule here, the bromine molecule here. As the reaction proceeded to an equilibrium, it created a large number of molecules of product, HBr. This particular equilibrium constant would have the product, HBr, squared from its coefficient, set over H2, the reactant, in a bracket for concentration, and multiplied by bromine, Br2, each of those powers of 1. Definitely going to be a number greater than 1 because I'm favoring the product side of equilibrium. And if we have a small equilibrium constant, we're favoring the reactant side. In this diagram, we have molecules of nitrogen, molecules of oxygen in far greater amounts than the 2 units of NO that are produced. I don't have very much product in this picture, so I'm going to end up comparing product over reactant and end up with a small value for the equilibrium constant. So the size of the number we find interesting. In this practice, we're being asked to write the equilibrium constant expressions and predict the position of the equilibrium for the following examples. I know the answers are right here, but let's at least talk us through. First of all, 2 units of SO2 are reacting with oxygen to form 2 units of SO3, a 2 to 1 to 2 stoichiometric ratio. Products over reactants, where the coefficients become the powers with which they're raised. So we would read this as the equilibrium expression. The equilibrium constant K is equal to the concentration of SO3 squared over the concentration of SO2 squared times the concentration of oxygen to the first power. Products over reactants, where the coefficients become the powers with which we raise. And look at the magnitude of the K. It's very large. This definitely is favoring the right side of the arrow tremendously. Very large number. And the opposite here, a very small number for your second example, to the negative 17th power is going to favor the reactant. That's a number much smaller than 1. So favoring the reactant side, we would read this as the equilibrium constant K is equal to the concentration